Welcome to the video on Clapp oscillator. The Clapp oscillator is a one kind of LC oscillator and it is similar to Colpitt's oscillator. To achieve high frequency stability, the Colpitt's oscillator circuit is slightly modified in practice called as Clapp oscillator. In this Clapp oscillator, it contains one additional capacitance connected in series with the inductor L. Okay, in the tank circuit of the Clapp oscillator, it have three capacitors C1, C2 and C3 and one inductor L should be connected. So the inductor L and the capacitor C3 which are connected in the series. The C3 improves frequency stability and it can be able to design at particular resonant frequency. So that is the small introduction about the Clapp oscillator, and next we are going to see about the circuit diagram of Clapp oscillator and we can discuss about the construction and working of the Clapp oscillator. So just see the circuit diagram. In this circuit diagram the transistor can be connected, so this transistor can be working in common emitter configuration, and here this common emitter configuration transistor which produces 180 degree phase shift, and this tank circuit, so this tank circuit of the Clapp oscillator which provides 180 degree phase shift. So the total phase shift of this circuit can be given as 360 degree. So in this tank circuit, C1 and C2 are connected and this C3 and L are connected in series connection. So this CC is nothing but as coupling capacitors. This CC and CB are the coupling capacitors. R1 and R2 is nothing but as biasing resistance which is used to bias the DC bias of the transistors, and VCC is the power supply. VCC is the power supply. RE and CE are the emitter resistance and bypass emitter capacitors. So this is the construction and working of this Clapp oscillator. Now you can see the operation of this Clapp oscillator. Yes, so this I explained before, this amplifier section, this common emitter amplifier section produces the 180 degree phase shift along with this feedback network. So this tank circuit is called as the feedback network and also produces 180 degree phase shift. So the total phase shift is 360 degree. The necessary condition for sustained oscillations is satisfied. In case if the feedback is adjusted, so that loop gain should be A beta equal to 1. So according to Barkasian criterion, the first condition is what? Modulus of A beta equal to 1, and the second condition is the total phase shift of the loop is 360 degree. Yes. Now we are going to discuss about the derivation of frequency of oscillation. Right. So first of all, this equation is what? The general equation of LC oscillator. So this is the master equation for LC oscillator. It is common for all the oscillator like Clapp oscillator, Colpitt's oscillator, Hartley oscillator, for all these LC oscillator, and this is the master equation: HFE into Z1 Z2 plus Z3 Z1 plus Z1 Z2 plus HIE into Z1 Z2 and Z3 equal to 0. So to find the frequency oscillation we should equate this imaginary part equal to 0. Okay, so before that we should substitute the value of Z1, Z2 and Z3 in the master equation. So let the value, as I told before, Z1 and Z2 are the capacitors of C1 and C2. Z3 is nothing but as the capacitor C3 which is connected in series, okay, series with the inductor. So Z3 equal to inductor plus capacitor C3. So the value of Z1 equal to minus J by omega C1. So it is also called as Z1 equal to 1 by J omega C1. That equation can be rewritten as minus J by omega C1 because we should always use the imaginary value in the numerator. So Z1 equal to minus J by omega C1, Z2 equal to minus J by omega C2, Z3 equal to J omega L minus J by omega C3. Now we can substitute these three values in the above equation. So after substituting the value we can get this equation like this one. Okay, so minus HFE divided by omega square C1 C2 minus 1 by omega square C1 C2 plus L by C1 minus 1 by omega square C1 C3 plus JHIE into minus 1 by omega C1 minus 1 by omega C2 plus omega L minus 1 by omega C3 equal to 0. So this fourth term is your imaginary term. So to find the frequency of oscillation, we should make this term equal to 0. We should make the imaginary term equal to 0. So now minus 1 by omega C1 minus 1 by omega C2 plus omega L minus 1 by omega C3 equal to 0. Okay. So after simplifying this expression, we want to find out the frequency of oscillation F. Now omega square L equal to 1 by C1 plus 1 by C2 plus 1 by C3. So these three capacitance 1 by C1, 1 by C2 plus 1 by C3 can be combinedly called as 1 by C equivalent. Okay. So C equivalent is nothing but as equivalent capacitance. So C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. So I am going to apply this C equivalent for this equation. So omega square equal to 1 by L C equivalent. Now the omega value can be given as 2 pi f, right? So now what is f? F equal to 1 by 2 pi root of L C equivalent. So C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is very important equation for Clapp oscillator. And next we are going to discuss about the condition for oscillation. So to find the condition for oscillation, we should make the real part should be 0. Okay, in this fourth term, the first three terms are real part terms and the last fourth term is the imaginary term. So we should make the real part term equal to 0. So minus HFE omega square C1 C2 minus 1 by omega square C1 C2 plus L by C1 minus 1 by omega square C1 C3 equal to 0. So now C3 is used for tuning purpose and hence can be neglected. So we should neglect this C3 value because C3 is a tuning capacitor. So it is used for setting the desired frequency range. Okay. After neglecting C3, we can get this equation as this one. And after simplifying, we should find out the value of HFE. Okay. In this equation, we should find out the value of HFE, forward current gain. So finally we can get the equation as L omega square C2 equal to 1 plus HFE. Now you can substitute the value of L omega square. So before we should find out the value, right? So omega square L equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now substitute the value here. So after substituting the value omega square equal to 1 by L into 1 by C1 plus 1 by C2, we can get this equation as C1 plus C2 by C1 C2 into C2 equal to 1 plus HFE. So this C2 and this C2 will be cancelled. So finally 1 plus C2 by C1 equal to 1 plus HFE, and this one will be cancelled, and finally HFE value should be given as C2 by C1. And finally we are going to discuss about the advantages of Clapp oscillator. What are the advantages of Clapp oscillator? So the frequency is stable and accurate, and the Clapp oscillator having a frequency stability, and the stay capacitance have no effect on C3, which decides the frequency, because the C3 capacitor is called as a tuning capacitor. Okay, so which decides the resonant frequency. And finally, keeping C3 variable, the frequency can be varied in the desired range. So that is the advantages of the Clapp oscillator. Thank you.